Thank you, Dirk, and thank you very much for all the organizers for making the effort to organize this very nice online gathering, and for this opportunity to talk about current magnetic effect here. So this is the outline. I will give a very brief introduction and then go through a number of topics. But let me make a disclaimer first that I don't think I really intend to give a sort of comprehensive review talk. I would just sort of more trying to give a very short sketch of what are the relevant and important issues and what are the interesting development from my personal point of view. And there are many exciting progress, and there's the list of all kinds of reviews. I mean, broadly defined and related to the chirality, vorticity, and magnetic field. And many of the authors are here actually. So these are all excellent sources if you want to find more information. So this, I really like the title of this workshop. It says spin and hydrodynamics in relativistic nuclear collision. And I think it rightly hit on all three key elements that I think are very important right now in the field, and that's the spin and the hydro and the collision. Indeed, so I think since last year or so, in many talks, I've been trying to advocate that in our field, we're getting into a new paradigm of considering this quark-gluon plasma or fireball in the nuclear collision as the spin fluid. In the past 2 decades, I think we have been mostly focused on the transport of energy and the momentum in this hot matter. Okay, and that was very, of course, successful. People were able to extract important property like shear viscosity and was able to claim that our QGP is actually the best or nearly perfect fluid. It's only like in the last several years that people start to really pay more attention to another important degree of freedom in the fluid, and that's the spin. And the quark carries spin, of course, gluon also carries spin, but gluons are elusive to probe. So we can more easily probe quarks, and of course the hadron derived from quarks. And they carry spin, and that spin can be probed by a number of external handle that we have, and that's basically the chirality, vorticity, and magnetic field. Spin is a very interesting quantum property. If you don't measure it, if you don't look at it, it can be in any direction. But if you provide an external probe like chirality, vorticity, or magnetic field, it will be polarized along that direction. Okay, and that's the way people have been playing with spin all the time. Dating all the way back to the beginning of quantum mechanics, like the Zeeman effect, and then condensed matter, paramagnetism, and all that stuff. And people have had a lot of experience about how to play and probe the spin. In our environment, in the heavy-ion environment, I think in recent years, there have been a lot of development on that, okay? We started to realize that the interplay between spin and those external probes like chirality, vorticity, and magnetic field can lead to many novel phenomena. And this talk will focus on one example, and that is the chiromagnetic effect in heavy-ion collision. So this is sort of just a very general, broad discussion. And I think that's pretty much the main focus of the workshop, namely, we want to understand how the spin degree of freedom behave in our QGP fluid under the influence of chirality, vorticity, and magnetic field. Now, chiromagnetic, I think everybody in this conference, of course, knows very well what it is. I don't want to spend too much time to explain what it is. Just want to briefly say that it's certainly a very interesting physics. It involves, the chirality of our quark system, the anomaly that can generate this effect, the topology of gluons, which of course in turn generates that chirality in the first place, and the extremely strong magnetic field in our heavy-ion collision system. And this is by itself is a generic anomalous transport process that give the electric current, or more generally vector current, under the presence of magnetic field. It's intrinsically a quantum mechanical transport process. So many interesting aspects of it. Of course, it has been studied for, by now, almost like 15, 20 years. I just want to provide a simple intuitive picture of CME in terms of the spin polarization idea that I mentioned earlier. Indeed, what is a current magnetic effect? It's a vector or electric current along magnetic field, which normally wouldn't happen because obviously a B field is a pseudo or axial vector, and the electric current is a vector. So normally they wouldn't be parallel to each other. But here is a simple way to understand why something like this happens. Now imagine that we have a system of quarks. They have spin and they have momentum, and suppose they're massless. Now if you apply a B field, that will basically polarize spin. Now for simplicity, let's say suppose we have only positive charge quark. Then spin will be preferably aligned with magnetic field. And this is just magnetic polarization, okay? Spin parallel to magnetic field. Now, if on top of that, we do have non-zero chirality of the system. Let's say imagine an extreme case, we have only right-handed quarks. Now in that case, the spin is gonna be correlated with momentum. And this is just chirality polarization. Spin and momentum are parallel to each other. As a result of that, and with the help of spin, now we have a correlation between magnetic field and the momentum of the quarks in the system. Basically, momentum is parallel to spin, and spin parallel to magnetic field. So in the end, the quarks have momentum that are preferably along magnetic field, which means there is a current along magnetic field. Now this is a very intuitive way of understanding what happens in CME, and it does reflect the two important elements here: the magnetic polarization. That's why we need the magnetic field B in that formula. And then the chirality polarization, that's why we need the axial charging mu5 or N5 in that formula. Okay, and of course the coefficient is harder to fix in this picture, but the coefficient also is very important because it's universal, and that's basically a reflection of a chirality, anomaly, of the fermion, the massless fermion. Okay, before I go to more specific discussion in High-valence collision, let me just really mention in passing that there's strong interdisciplinary interest. There are people from condensed matter who study CME and semimetals, astrophysics, cosmology, plasma physics, and even quantum information. There are many interesting developments, and I don't think I will have the time to discuss this, but I think this is showing us that the physics of CME is rich, and it would be great if we can really discover that effect in High-valence collision system. Okay, so as I said, so by the way, so if you have questions, feel free to interrupt me. Now there are a few elements for chiral-magnetic effect. We need chirality and we need magnetic field. So I'm going to first briefly talk about chirality and magnetic field, and then I will talk about the effect itself. Chirality. So I think just to remind everybody that that's actually why the whole field initially got interested in this, and that I think was pioneered by Dima Kajeev here, who in his 2004 paper basically had this initial idea that if we want, topology of course is very important for gluon field, like instantones, phanerons. Those are important for the non-perturbative dynamics of QCD. But gluons are hard to probe, okay? There's no easy way to see the effect directly from gluon. On the other hand, because of the anomaly that the topological fluctuations of gluons can be reflected or directly connected to the chirality fluctuation of the quarks in the system. And that provide a way to access the topological aspect by checking the chirality of the system. Well, how can we check or probe the chirality of the quark system? Well, that's where the chiral-magnetic effect will be useful. The chiral-magnetic effect directly depends on a non-zero chirality. So if we can, characterize the chirality through this chiral-magnetic effect, then we have access to chirality and ultimately to the topology. Now it's really actually, you can see that here in this chain of argument, of course, the trouble is that we don't know how much chirality or axial charge we can get in the system. And the chiral-magnetic effect is supposed to provide sort of a measurement method to quantify that. So in this sense, it's really important if we can find some independent probe of axial charge, axial current, and that can help us to constrain better the chirality and the chiral effect. So, and that I think in this workshop, we already heard a number of talks where connections are being made to, between the actual charge and observable like polarization and helicity. I think last week there was an interesting paper by Francisco and collaborators where they tried to propose a way of measuring actual charge through the helicity correlation. And I think these are going to be discussed in the talks, for example, by Matteo later, and also was touched on by other speakers at this workshop. But I think it's, my message is here that it's important if we can find different ways other than the chiral effect to access that actual charge. Now, chirality also provides an interesting playground for many-body theory, and that's particularly reflected in I think, like hundreds of papers in the last couple of years about this chiral kinetic theory or quantum kinetic theory, which incorporate the H-bar quantum effect into the classical Boltzmann transport. So this was the early form of three-dimensional chiral kinetic theory that were developed by a number of people here. So basically, you can see that it's very similar to the classical Boltzmann, except that the kind of semi-classical H-bar order effect is encoded through the equation motion on the second line. Okay. However, I mean, it was noticed that in this kind of formulation of kinetic theory, there was some funny issue about Lorentz covariance. Well, these equations were also sort of studied by condensed matter people, but they perhaps don't care about Lorentz covariance at all. But for us, we think this is important. Indeed, pointed out in the paper by Song and collaborators, that this distribution function, which should be a Lorentz scalar quantity in the classical case, is no longer a scalar quantity. And also, when you are trying to think about collision of two particle or frame transformation, you need this so-called funny side jump. Well, these were already mentioned in, I think, in some talk yesterday on Tuesday. But really, we don't have a clear picture why, or we didn't have. And now, precise, I believe we generally understand why. But at that point, a few years ago, I think it was very confusing. And indeed, this really is again reflecting the fact that chirality and spin, the correlation due to chirality brings some interesting theoretical issue. This sort of is really a clash between spin, momentum, and chirality. When you do a frame transformation from one frame to the other, well, momentum is always a Lorentz vector. There's no negotiation about that. Now, chirality for massless particles, chirality is actually a Lorentz invariant property. Namely, if you have a right-handed fermion to start with, you boost your frame, it's still going to be a right-handed fermion. Doesn't matter how the momentum or spin are transforming, it's still going to be a right-handed fermion. What that means is that your spin transformation actually is totally fixed by momentum and chirality. After the boost, your spin is still going to be along momentum. On the other hand, remember, spin is part of the angular momentum. Angular momentum had to transform a tensor. It's a Lorentz covariant quantity. So that means there must be a clash. Okay, the spin has to follow momentum, where the angular momentum follow its own transformation. So how to reconcile that? There's only one resolution, and that is to dial your extra orbital angular momentum, or to be more precise, you need some ambiguity in your position, which of course in turn give you extra orbital angular momentum to make this work. And that's indeed actually rightly so, because in quantum mechanics, if we have a momentum state, we don't have a well-defined position. So that's all fine. Actually, it actually works out. But from a theoretical point of view, it's still kind of troubling, okay? Because as we all know, I mean, in principle, transport theory doesn't have to be like a three-dimensional, transport theory. It can be formulated entirely in a covariant way. So why somehow suddenly there is a non-covariance issue? And where and how exactly this non-covariance issue arises? And that I think triggered me to look into this covariant chiral transport. Of course, there's a whole long history of that in the framework of Wigler function formalism. Back in the 1990s, there were early works by people like Miklos, Uli, Vasak, Ponfei, and so on. And more recently, in the chiral transport context, I think there were earlier works by Chun Wang and collaborators, Hidaka, Shipu, and Dilun Yang, and others. And we also had a paper in early 2018. And there are many talks, I think, at this conference about this topic, the covariant chiral transport. So what I want to sort point out here, which was, of course, reporting our work back in 2018, that is that where does this exactly come in, namely the frame dependence or non-covariant issue come in. And also at that time, we were having in mind to have a proper Wigler formalism treatment in the matrix case. So that's what was done in this work. It turns out that the key step where the frame dependence comes in is at H bar, when you try to decompose the current J at H bar order. Now, some of you perhaps are familiar with the Wigler function formula, and some are not. But in general, you do a semi-classical expansion of physical quantity. Let's say the chiral current, right-handed current or left-handed current. The zeroth order is the classical current. It's just the momentum of the particle. P mu is parallel to P mu. And then in the next order, that's the first order or H bar order. Your current has a H bar order correction, and that is not exactly along the momentum direction. You have other quantum effect that comes in. Especially when there's the internal electromagnetic field. Now, when you try to decompose that first order correction, you would have a piece that is parallel to momentum, P mu, for momentum P mu. And you would have, so if you want to separate that piece, the piece that is parallel to P mu, this is where it becomes frame dependent, okay? And you may wonder why people want to do that, why you need to decompose this H mu here. That's because people typically try to make a contact with the classical transport theory. In the classical transport theory, the current, particle current, is P mu times the distribution function F. Now, if you want to say, I want to define some, still a semi-classical distribution function F with the H bar order correction, which is the F chi1 here, then you have to separate that piece from the first order current, namely the piece that is parallel to P mu. And then you can call the rest to be quantum correction. That is not related to the particle number, okay? Now, this is exactly where you introduce frame dependence, because if you want to unambiguously define your first order correction to distribution function, you then have to fix this K mu, the four vector K mu, to be precisely having 0 time component, and then a 3 component K that is the perpendicular to 3 momentum P. And remember, 3 momentum P of course depend on the frame of a particle. So that's where you introduce frame dependence. Now, I mean, you don't have to go into the technical aspect. All I want to say here is that in principle, you don't need any distribution function concept. You can just do fully covariant current and everything. But if you want to make a contact with classical Boltzmann and define a H bar order distribution function, that's where you introduce frame dependence. So I think after that, I mean, we also understand that there's this famous M mu vector in the general solution of K mu that actually plays the role of choosing the frame. It should be identified as the 4 speed of the frame that you choose. So I think that has been clearly understood. Okay, this is one example where I think chirality brings interesting physics insight. I mean, this has nothing to do with phenomenology. It's just sort of, I think, theoretical understanding of many-body system for massless fermions, which I think is quite interesting. Okay, so now let me move on to magnetic field. That's another important element for CME to happen. Okay, so I think I don't need to say too much here. Everybody now knows that due to the initially fast-moving ion which carry large positive electric charge, there is a large, first of all, there is a large angular momentum, and second, there is a strong magnetic field. So on the right, I'm showing you a simulation results for magnetic field direction and strength in a semi-central collision at RIG for gold-gold. You can see in the center part where you have this dark blue, this is where the fireball would be. The magnetic field on average, this is averaging over many events. from initial Monte Carlo Glauber, you can see that the magnetic field is relatively homogeneous in the middle part of the fireball, and the strength can be about a few times m pi squared. So this certainly important. This certainly very, very strong field, and that can induce, hopefully observable effect, not only current magnetic effect, but also other magnetic field related effect. There are two important issues I want to emphasize about the magnetic field. The first thing is that there is actually an important azimuthal fluctuation. Although on average, this magnetic field is perpendicular to what we call the reaction plane, which is the idealized concept or more theoretical concept. But in reality, when our experimental friends do measurement, they often identify the so-called participant plane, and that fluctuates from event to event. And our magnetic field also fluctuates from event to event, the direction. So this, I think, is actually important to understand and to quantify. The other important thing here is the time evolution. I just said that the magnetic field is strong, but that's only for the initial, very initial magnetic field. What happened to that magnetic field after the initial impact is still a big question, okay? So let me briefly discuss these two issues. For the first issue, I think I repeated emphasize that this was studied actually a long time ago in this paper from 2012 with Guang and other collaborators. I think we were perhaps the first to point out that you have to take into account this azimuthal fluctuation of magnetic field direction, okay? So these are some detailed simulation results showing you that, for example, in central collision, magnetic field is pointing everywhere. It's not correlated with your geometry, or in semi-central to peripheral collision, the magnetic field is on average correlated with your participant plane, but still there is a sizable spread. So you cannot ignore that, okay? The other important point that we emphasize in that paper is that you have taken into account the finite size of the proton. Otherwise, your calculation of magnetic field strength would very much depend on how you make a UV cutoff of your Coulomb singularity. Okay, so that's unphysical. So you really have to take into account the charge radius of proton. Okay, so one important thing I think that people learned from that paper later on is that the magnetic field actually had different angular correlation with the reaction plane and with event plane. Okay, it actually is better correlated with the reaction plane and is less well correlated with the event plane and is not correlated at all with the triangular plane. Now this now becomes a very valuable feature for validating any signal that it should be induced by a magnetic field, and experimentally do use this to help separate signal and background, and I will mention this again later. Now, time dependent, this is a much harder issue, okay? I think for the azimuthal fluctuation, I think now people are confident that we can quantify that, and we can even make use of that as a valuable feature, as I said. But the time evolution is still very, very challenging. How that, of course, the initial ion after the collision will just fly down beam pipe, so the magnetic field in the central rapidity will quickly decrease. That's what people refer to as the vacuum piece of the magnetic field. The question here is that whether the medium response could possibly make that magnetic field live longer, because we have a conducting system with quarks and possibly with the electron, positron, all that stuff in there. And the question is whether that makes the magnetic field live longer, okay? There are different regimes that you can study a magnetic field together with a fluid, okay? The first regime is, let's say, quite strongly coupled or more ideal regime, namely the magnetohydral regime. I think there are excellent works by several groups. For example, here I'm showing you one plot from Gabriel, Francisco, and collaborators, the EcoQGP-based calculation. Now, here I think one important thing that we should realize that for magnetohydral and especially ideal magnetohydral to work or be applicable, you need a very large conductivity. And this actually certainly is a question mark for now, because we know that if you trust the lattice calculation in the quantity limit, we don't have too much conductivity here. Another regime is a linear regime. That's where your B field scale is still kind of small compared with your medium scale, and the B field has very little influence on the bulk evolution. In that case, you can treat the B field as a sort of perturbation on top of the bulk. The bulk, expand in its own way, and then you can solve Maxwell equation for B field on top of that fluid. Okay, There are going to be talked by, for example, Gabriel and also by Koichi, and there are many other works that I didn't have time to discuss. There are so from the magnetohydro regime, if you want to say, well, I want to take into account viscous correction, then you need to go beyond the ideal magnetohydro. I think there are interesting development from their kind of collaborators and from other people about framework development for viscous magnetohydro. I think that these are quite interesting. Of course, to make this or to convert this theoretical result into a phenomenological modeling, I think there's still a long way to go. But theoretically, certainly these are important new results. Now let me talk about the other approach, namely to just solve Maxwell equation on top of a charged fluid. Okay, so this seems to be perhaps a more realistic way of doing the modeling of magnetic field, dynamical magnetic field in heavy-ion collision. There were some of the early works, for example, by especially I think Gorsoy and Dima and Trenson and Krishna and so on in this 2018 paper. That was quite good because I think it was the first try to solve Maxwell equation on top of evolving hydrodynamic medium and a realistic hydrodynamic medium. It's good because, as I said, it's a realistic fluid. I think they use the bulk evolution from visual hydro. On the other hand, there's some problem because the result is based on unrealistic assumption. Essentially, the magnetic field is not directly solved, and it's using, I think, an analytic solution from Chin and others, where you have an analytic solution by assuming the medium is there and not changing with time and space from infinite past to infinite future. But unfortunately, that's of course not the case for heavy-ion collision. For heavy-ion collision, we do have sort of a switching on of the medium. Before that, there is no medium. So that's an important thing that you have to overcome. There are also other interesting works by solving dynamic magnetic field, taking into account the CME transport current itself. Okay. And you do see some difference in the case with and without CME current. Okay, so this is something that we recently have made a lot of effort on, namely to have a more realistic approach of dynamic magnetic field. We want to solve the magnetic field Maxwell equation on top of a realistic fluid, and we want to we don't want unrealistic assumption. Okay, this is technically quite challenging. I mean, the physics is clear. You have a magnetic field and electric field that evolve according to Maxwell equation. You have a medium that provides current. That medium itself is evolving according to hydrodynamics. Okay, we have established a code that is quite robust. We tested that code with the Bjorken expansion, Gupser expansion, and the music hydro, and it's working very stably. And I think the results make a lot of sense. So we start with vacuum. So before time zero, there is no medium. There's only vacuum. Okay. And then after the collision, there's a short pre-hydro stage where we don't know for sure how to treat the medium effect. So this is some small uncertainty, not small, some uncertainty we're still trying to figure out. And then there's the hydro stage where we have the conductivity with the medium that changes with space and with time. It's just from the background hydro. Okay. We found that actually longitudinal expansion is very important. It has a lot of impact on how the magnetic field evolves. The transverse expansion doesn't have too much of effect. And that's understandable because transverse expansion kicks in much later after a few Fermi, by which time the magnetic field is already small anyway, okay? So here I'm just showing you a few quick results. If you, you can see the results very strongly depend on the conductivity of the medium, which of course is not surprising. You can see that if you have a conductivity that is like the QCD at 1 to 2 TC, which means that it's kind of small. So sigma over T is about 0.1, and you don't have, and you can see that the magnetic field already dropped by several orders of magnitude by 1 Fermi over C time, and it deviated from vacuum only after that time. Okay, Now, if you have roughly the sigma of QED, okay, which means sigma over T is about 100, then indeed the magnetic field can be saved and live longer. And you can also see between left and right, what's the difference between left plot and right plot. Well, that's whether you put in a pre-hydro conductivity or not. Now, pre-hydro means that, of course, we're in the pre-thermal equilibrium stage. But remember that quarks are produced, I think, quickly after the initial collision. And there will be some conducting effect, even though the system is out of equilibrium. So let's say effectively you're putting in some conductivity for that 0.1 to 0.4 Fermi, and you can see that immediate help, okay? So what's the message that I want you to take away? I think the message is that really we just need a little bit of medium help at the early stage before 1 Fermi over C, okay? That means the pre-hydro effective conductivity is crucial to calculate the dynamic magnetic field. Also, at the very beginning of your fireball hydro, the sigma QCD at a very high temperature end, about 3 times TC, is perhaps also important. So we have this machinery that is ready, namely to solve dynamic magnetic field Maxwell equation on top of a realistic hydro. But we now need sort of better physics input, namely like the connectivity. We are also trying to, yeah, go ahead.
Yeah, can I ask a question? So if you could go back a couple of steps, a couple of slides. Not here, but yeah, so I didn't really understand what you were referring to when you said unrealistic assumption in that calculation with
You mean this one?
The previous one.
Yeah. So remember I said that you need to solve Maxwell equation. They didn't really directly solve Maxwell equation. They take a solution for a particular situation that has a charged particle in a medium, in an infinitely large, homogeneous, constant medium.
Well, yeah, but that has to be integrated over, right? So the source is finite size in this work. Well, by the way, I am one of the authors, so I.
Yeah, sure. No, but what I mean unrealistic is the medium itself. You know, that solution. My understanding is that solution is valid if your medium is like there forever, right?
No. It has to be so. Well, it is. So the only thing that is not taken into account here is the formation period of the medium. So that we have no idea about.
That's exactly what I mean. That
right. Yeah. No. Yeah. Sure. So I have another related question to that. So when you go go to your work in this calculation, so yeah, next slide maybe. I was wondering so because these conductivities, as you see here, temperature dependent, and temperature depends on time. Can you have you taken into account the time dependence of the parameters?
Very good question. Sigma certainly changed with time. You know, so basically at every time step, you have a bulk hydro background. You have the temperature of each spatial point at each time, and I take the sigma corresponding to that temperature.
Okay, perfect. So the sigma, the parameters depend on time here.
Yes.
Yeah. Great. Okay, yeah. So that's.
The only thing, I mean, potential issue here from a theoretical point of view is that, of course, it could be that we're not exactly in the DC regime. We could be in an AC regime, and that's a question we don't address now. Yeah.
Okay. Yeah. Okay. Thanks.
Okay. So I think anyway, so we're progressing on this, and we're hoping that this can eventually be figured out, namely how the magnetic field evolve dynamically, and for that certainly we need some better estimate of the pre-hydro quote unquote conductivity, which perhaps will be very, very crucial. On the other hand, of course, we can also think about connecting B field with other observable. Of course, I should say that there are many other works that try to point out magnetic field effect in observable, like for example, d meson flow, charge d meson directed flow, the dilepton production, and so on. So I haven't had time to discuss all this, but let me just mention that there are many interesting effects that can be induced by magnetic field apart from CME. This is another example, namely the polarization. I think we already had a lot of discussion at this workshop, and will be discussed more at this workshop, Namely, there's this funny splitting between hyperon and anti-hyperon polarization. One possible explanation is that this is due to a magnetic field. Well, this, I think, by Mueller and Andres Schaffer first had this paper pointing out that possibility. They only made, of course, a very simple estimate. They're saying that this put a constraint on the magnetic field lifetime to be about 1 Fermi over C at 200 GeV. So that's, of course, one interesting possibility, okay? The trouble here is that you can see this is really sort of trying to constrain the magnetic field at late time, because all the hyperon, anti-hyperon, they are produced relatively late, at least several Fermi into the time evolution. So they provide a handle to constrain the late time magnetic field. Now, suppose we take this idea and we assume that the magnetic field indeed can account for the observed splitting between hyperon and anti-hyperon polarization. Then we went ahead and did some quantitative simulation within the AMPT framework. Well, you all know that AMPT can already explain the overall polarization, let's say average polarization of lambda and anti-lambda. Now we put in the magnetic field, we compute the magnetic additional polarization from magnetic field, which is opposite for hyperon and anti-hyperon. Anyway, so let me skip the details. So in the end, if you can, and we tested 3 different kind of time evolution, because we don't know the precise time evolution. We just use some parameterization with the lifetime parameter. The short message is that if you want to explain all the observed splitting with a magnetic field at late time, you would see that the time, the lifetime of that magnetic field had to be scaling like A over square root beam energy, square root SN beam energy. This parameter A, the best fit for that is about 115 plus minus 16. Now, is this large or small? Well, it does require some sort of medium help to make the magnetic field live longer, because if you compare it with a vacuum magnetic field, which can be estimated by basically the nuclear overlap time for the 2 nuclei to pass each other, and that scales about, I think, 25 or 26 over square root SNN. So it's about 5 times the vacuum lifetime. Now, I think this estimate is not unrealistic, because if you look at 200 GeV collision, which means the square root S is 200 GeV, and this parameter A is about 100 GeV times Fermi over C, which means that at RIC, really, you have about 0.5 Fermi over C lifetime, which I think is enough, okay? So I think it could work, okay? At low energy, it's different. At low energy, you know, as you can see from this fitting, at low energy, if you want to explain that observed splitting, you would have to have magnetic field that is, you know, 5 to 10 Fermi, you know, lifetime, which is not easy, okay, for the initial magnetic field. So we were thinking about what could provide a late magnetic field at low energy. So one of the idea that we proposed in this paper is that, you know, our fluid is really a charged fluid that is spinning itself, okay, rotating around. And that's actually by itself a way of generating magnetic field, apart from the conductivity mechanism, okay? So this is a different mechanism. It's just you have a fluid, you stir it up and it is charged. Then you have a magnetic field. We have some pocket formula here to estimate that magnetic field from this rotation or vorticity of the fluid itself. And of course, multiplied by the charge density of the fluid. So we made some estimate. We think that they could be contributing a fraction of that observed splitting, okay? Now, of course, whether this works or not quantitatively, we don't know at this point, but that requires further work. So finally, let me come to CME. I have another 5 to 10 minutes. Let me very briefly say what's going on now with the CME. So I already talked about Chirality magnetic field. So now really coming to the business in the last 5 minutes, the CME experimental status. I want to skip this because everybody knows what I'm trying to say here, that namely we want to observe that CME charge separation through the charge dependent Azimuthal correlation. Namely, the same sign particles are preferably emitted one way and negative particles emitted another way. And a number of experimental observables were designed, okay? There are all these correlators. Now, what is the status? Well, first measurement since 2009 by STAR. In the past decade, and a lot of effort were made experimentally by STAR, by ALICE, by CMS at both RIC and RHC. The search happened from 10 GeV to 5,000 GeV beam energy. Various colliding systems have been looked at, including PA, DA, kappa kappa, gold gold, uranium uranium, and lead lead. The trouble here is that the signal basically is positively correlated with the magnetic field strength. The magnetic field strength, on the other hand, is positively correlated with the elliptic shape of your fireball. The elliptic shape, of course, is positively correlated with the elliptic flow. And finally, the elliptic flow is positively correlated with the background correlation. Okay, background is driven by elliptic flow. They are roughly linearly proportional to each other. So that's why it's so hard to separate the background from signal. Okay, it proved to be a very difficult search after 10 years of effort. And also the other reason is that we have a situation that that the signal is relatively small, whereas the background is relatively strong. Okay, so that's why it has been so difficult and why we haven't been able to conclude that search. Now this is the status. I think by early 2019, there are all this extraction. So what people did is that they try to separate background from signal, okay, with various ways. I think the message here that look like at RHC energy at either ALICE or CMS measurement seem to suggest that the signal could be very, very small or almost zero. That's perhaps reasonable because the magnetic field, as we said, will be very, very short. It's just like a really short pulse at RHC energy. At RHC, I think the latest status was reported at Quark Matter last year. I think according to STAR, the result is that out of all the measured correlation, there is perhaps about 8% that could be due to CME. Of course, the error bars are large, both statistical and systematic error are large. And these results are often model dependent in the sense that you have to make certain assumptions about how the background change, okay? So the challenge is that you need a very sensitive observable, or you need an entirely new approach, and that's the Isobar collision. I think the Isobar collision has a very basic idea, and that is to contrast two systems with perhaps the same or identical background or different signal. Okay, there was a very successful data taken around in 2018, and now I think the parameters are working on analysis. So this is a projection plot from Gang Wang and Ai Hong Tang. You can see that if we, so this is based on the fact that actually STAR collected about 2.5 billion good events for each colliding system. The y-axis is about the relative difference between the two systems. That depends on how much background you have. You can see in this plot, I hope you can see here, in here, this is a schematic, okay? Now, if the background is, let's say 100%, of course, then there will be no difference between ruthenium and zirconium. On the other hand, if the background is limited, then we can see a visible difference between ruthenium and zirconium, okay? So that's the idea. So you can see that here, if you do have a, if your background is not more than 86%, okay, then you would have a chance of 5 sigma significance to see the difference between ruthenium and zirconium. I think that's very good. Of course, as I said, STAR right now, the projection is right around here, right? It's like 8% of signal, which means about maybe 90%, but there's large uncertainty, of course. So we are perhaps around this region. So I think the chance is good. So this, some update from Ai Hong by September 2020, namely where they are in terms of analysis. They are here, okay, you can see we're here, meaning STAR is here. I think that's pretty good. Namely, they're in the actual blind analysis, and perhaps in a few months, okay, they will have a first pick as a result after unblinding. So I think that's quite exciting, okay? We're almost there after a long wait, like almost 2 years. There are a total of 5 groups within STAR that are doing the blind analysis. By blind, that means they don't know what they are analyzing, whether this is ruthenium or zirconium. So that, I think, is the best way to avoid any potential bias, okay? So which is a very good approach, a very professional approach. So the 5 groups are using these observables to do that analysis. There's one no blind analysis with the sign balance function. So with all the 6 different analyses, I think the hope that we can see a coherent message coming out of that, okay? So and that's actually quite exciting. I don't want to go into the details of the observables, but just want to say that the experimentalists spend a lot of time and effort to understand what they should expect if there is a signal. Okay, I just want to make this message simple. Okay, so I think the number one step for all this whole thing is that you want to see a statistically significant enough departure from pure background. That's all we need. Okay, what that mean? Well, if you have 100% background, namely you don't have these unfed black bars here, then that means ruthenium zirconium will be the same in terms of measurement. Okay. Now, if there is any non-zero signal, okay, you should see a difference of ruthenium zirconium. If you have a statistically significant, finding that they are different, then I think that's we are at least halfway there. Okay. So I think that's what we should really wait for. Okay. There's some issue that a number of people discuss in the field, namely whether the background are exactly identical or not between ruthenium and zirconium, and that's due to some uncertainty in the nuclear distribution. I think, for example, Fuqiang Wang and the collaborators and Hannah and other people, they pointed out that it's not clear whether the background will be exactly the same, and that's true. Actually, that's issue is actually important. So we have proposed some strategy to overcome that issue. Then you can apply a joint multiplicity and elliptic flow cut for the event sample. By doing this, you actually can make sure you have two colliding systems that have exactly the same multiplicity and elliptic flow. Okay, and that you avoid the issue. So I think I perhaps should stop in a minute or two. So I think the other important thing to help our experimentalists is to develop quantitative modeling of CME. And I think there are different approaches based on hydro or based on transport model. You already heard talk about Yifeng yesterday on Tuesday for the transport model. So I'm going to briefly show you this so-called Alom's viscous fluid dynamics framework. That's I think in my view is the state-of-the-art tool to figure out or to make a quantitative prediction for the CME. Okay, I think we have this very useful tool now. There's 3 versions that have been developed, and I think on this the Shu De made a lot of important contribution here. So Shu De was a student at IU, and 2 years ago he moved to McGill as a postdoc, and we already had the first generation of AVFD, which is smooth hydro. We have a second generation, which is event by event, which also implement all the necessary background effects, including the hadron resonance decay and also the local charge conservation. So this is the version that we have shared with STAR actually for their observable study, and they found this to be very useful. The final generation is going to come out soon. We'll make that code package public in the near future, and that incorporate all the sort of state-of-art elements. I think this should be precise enough. Okay. So I'm going to skip this. I just want to show you a really important last 2 slides. That's the prediction for isobars. So the first here, I'm showing you the prediction for gamma and the so-called gamma and delta correlator with respect to the event plane. And that depends on the initial axial charge. The initial axial charge is the real theoretical uncertainty here. Okay. We don't know how much axial charge we have at the beginning. Okay. But the signal, if you do a subtraction between ruthenium and zirconium, okay, you will get the signal that is basically quadratically depending on that axial charge. So this is the gamma correlator, this is a delta correlator. They depend quadratically on the M5, initial M5. Now, if you measure both gamma and delta, you can easily identify where you can have a consistent picture. This is for pure signal. And after the isobar subtraction, you're supposed to left with pure signal. So that's one important point we've been making all the time. Namely, you do a subtraction and you check the consistency between gamma and delta. And you can take a ratio of gamma ruthenium minus zirconium over delta ruthenium minus zirconium. And that gives the ratio, which is basically minus 0.41 from our simulation. What is this ratio? This really is really just the decorrelation between magnetic field and the event plane, which if you do a simple initial state Monte Carlo Glauber, which is this number, very close to that final state number. So this is a very definitive prediction. And this ratio does not depend on initial axial charge. It's a very robust prediction. And you can do the same game for reaction plane. Now, the reaction plane, as I mentioned earlier, is better correlated with the magnetic field. So that's a good feature. Indeed, you can see if you do that measurement with respect to reaction plane, the delta correlate doesn't change, where the gamma correlator become twice as large. And again, they're both, depending quadratically on the initial axial charge. If you take a ratio, that ratio is minus 0.90. Okay. Again, this is basically reflecting that decorrelation between magnetic field and reaction plane. So this is another very robust prediction for the isobars. And there are other predictions as well, but I think these two are the most important. You measure delta gamma and delta for event plane and for reaction plane. Okay, so that brings me to my summary. I think I'm gonna skip reading all this. I just want to say the last sentence here. Stay tuned for hopefully exciting news from Isobar collision in just a few months. Thank you very much.
Yeah, thank you, Jinfeng. Very exciting talk and lots of new things to think about. So I now ask everybody to ask also as interesting questions as the talk was. So Sheming is the first. You think you have to unmute yourself.
Yeah, thank you. Yeah. Can you show slide 44, 45? Your prediction of gamma correlated. Does the figure obtained with certain assumption of the lifetime of the magnetic field?
Yes.
So what's the lifetime?
Okay, yes. So let me come here. So for all our three generations, if you read into the paper, we said clearly. So we use the parameterization, that is the B over B0. It's like 1 over 1 plus T over TB square. Okay, is this decrease, and TB is we use basically the hydro start time 0.6 Fermi over C. Yeah. This offers.
So that's a pretty long lifetime.
It's an important uncertainty, yes. Of course, the result would depend on that. It depends on two important factors: the magnetic field lifetime and the axial charge. But as I said, so from this part discussion, maybe I don't want to go back too much. So I think 0.6 Fermi is not short, but not terribly long if you trust all the
it's pretty connection
long. Between.
If you use realistic lattice conductivity, you'll never get such a long lifetime.
That's right. Yeah, I made that point, right? I said that what is crucial is just need a little bit of medium help. Yeah. At the very beginning, I agree with that. Yeah.
Can I make another comment? Or
sure. Very short one, yes, go ahead.
A very short one. You see, in a chiral magnetic effect, the whole purpose to search for the extra charge fluctuation or topological charge fluctuations. But you need a detailed knowledge of, you need a reasonable long lifetime for the magnetic field. That's why I always point out, I think Yifeng Zhang and we point out a year or 2 years ago, since we know the vorticity is large and has a much longer lifetimes. So we use vorticity to probe the topological charge fluctuation. Charge fluctuation is much a better way to look for the signal for topological charge fluctuations. And that we propose those up and down asymmetry, and you can do the R correlate analysis. You see similar signals, but a lifetime, no question of a lifetime. We use a realistic lifetime to evaluate that. Instead, in the magnetic field, in CME, you have to assume some magnetic field lifetimes. But for the up and down separation, you don't need to assumptions on lifetime of the vorticity because it's long. You can do self-consistent calculations. Then it gives you directly tells you the magnitude of the topological fluctuations just from the up and down asymmetry in the emitted particles. So, but somehow it's very disappointing. No experimentalists try to look for that signal.
Vorticity certainly, I mean, as I said or emphasized in this slide, it's important to find different observables that would be sensitive to the axial charge. and indeed, I think I'm aware that you and Yifeng have been working on this. Certainly, vorticity could be better in that sense, namely its lifetime could be longer. I think here, first of all, I think indeed experiments have not made a lot of measurements related to vorticity or chirovortical effect kind of process. Hopefully they will do that. Especially,
I think they are complementary. If you see the current magnetic effect, then you have to see the other effect.
We can also discuss this later. We have roundtable. Let's ask three more important questions. Gabriele.
Okay, can you hear me?
Yeah.
Yeah.
Good. Okay, so how do you compute the initial conditions of your magnetic fields? I mean, I see that you are using an analytic formula for the time evolution, but what is the spatial distribution of your initial magnetic field?
You mean in this part or in the?
I mean, you said, I mean,
yeah.
you've already run several simulations, so I mean, you need the initial magnetic fields, right?
Right now, it's still two separate pieces of work. So in this work, in this part, when I talk about dynamic magnetic field, so we recently established that calculation, the kind of code that will work well, but we haven't completed our integration with AVFD yet. So AVFD is a modeling that will deal with the CME transport. That I think will be done soon. So in this calculation, everything is just as realistic as possible. So you have the initial magnetic field from the moving flying ion, and then you solve that magnetic field starting from time 0 and on. So this I think is totally completely realistic for the magnetic field part. In our AVFD calculation, we just use a simple time dependence. Namely, in this part, we use a simple time dependence. The spatial distribution is still from simulation. The time dependence is just a simple parameterization. But what we eventually will do is to integrate this code with the magnetic field Maxwell equation solving module. Those two will be glued together. And then we have a fully dynamical calculation of both magnetic field and the CME current. Yeah.
Okay, then next question, Umut.
Yes, yeah. So I have a very short question. So the dynamical magnetic field calculation that you showed, have you looked at? So there are these recent measurements of the charge identified directed flow, both at RIC and LHC. Can you have you calculated those observables and just compared with the data?
Okay, that's a really good question. We haven't, of course. Remember that actually, I think you guys' paper was basically our starting point. So we certainly read and studied the you guys' paper, and that's where we try to improve that calculation of dynamic magnetic field. And indeed, our one of the thing we want to do is to make useful application to B field effect, like the directed flow. We haven't calculated that, but I think that's one of the interesting things to look at.
Yeah, it is interesting because we got the wrong sign. So
I'm aware, and I think as far as I recall, there's even a difference between the measurement by star and by ALICE.
Yes,
right?
yes. Yeah. Okay. Yeah. All right.
So that's certainly interesting to look at. Yes.
Yeah. And last question by Chun.
Yes. Can you go back to a slide? I forgot the page. It's saying that 86% of the signal indicate 5 sigma.
Okay. Yeah. I think I know what you want to look
5
at. Yeah, you mean this
sigma
one?
signal.
Sorry. Yeah. This
So
one, right?
Yeah. Can you explain it again? I didn't get the point. So what's the,
Yeah. Okay. So I think, I understand your question. So here, so what because I was perhaps a little bit in the rush. So this acts as the background level. Okay. So for example, if background is zero, so let's say this is our overall charge correlation measurement. Okay. This is, let's say this is the background.
Oh, okay.
This is the signal. Okay. Now, if background is 0%, that means this end is like all signal. Okay. This end is like all background.
I see. So
yeah. So if you have all background, of course, there's no way to see a difference. So this is like basically ruthenium zirconium difference. Okay. Now, if you have 100% of background, you will see no difference. If you have 100% signal, you will see a lot of difference between the two systems. Okay.
Yeah,
now
exactly.
We are somewhere around here. From our gold analysis, I would say we are perhaps around this region.
It's 80% of the background, right? Almost
right.
80.
What this means that if we have about 86% of background and 14% of signal, then the statistics would allow a 5 sigma identification of a difference between ruthenium and zirconium.
Ah, I see. So
yeah.
Of
course, if suppose we're here, let's say we're 95% background, then statistically, given the 2.5 billion of data, we probably will see a 3 sigma effect, for example. Yeah.
I see.
Yeah.
So you mean that it is hopeful that you can get the 5 sigma
well,
signals.
That nobody knows. That's precisely the issue. We don't know the background level. If nature is kind, then we perhaps can see a robust signal.
I see. But let me ask another question. So once you find the signal of the magnetic field, are you sure that's from CME?
That's certainly a good question. I mean, but that's like all kind of measurement. It's perhaps difficult to say I rule out 100% all other possibility. I think that's going to be hard. But I think given all the studies and I think if we say I cannot.
I mean the effect from the magnetic field is different from the effect of CME. So that's two different things.
That's true, but what we're looking at in this Isobar difference, it is a very specific charge correlation pattern, right? It's not some arbitrary effect. This gamma and delta correlator and all the R correlator and so on, they're built to see a charge separation. Okay, so it's not like it's not that every magnetic field effect will cause a charge separation, right?
Okay. So thank you.
Yeah. Thank you. One very quick question still by Ihong.
Yeah.
Jinfeng, very nice talk. So it looks like there's a substantial difference between second and the third generation of AVFD. You said the third generation will come out in the near future. Could you say a little bit more? What's the near future? This will help us coordinate, right?
It won't. I think maybe by near future, I mean perhaps a few months. But as I said, we already checked consistency across generation. So why? So you can see between second and third, we switch visual to music for the bulk hydro, but that's really more of other consideration. Namely, the whole best collaboration want to a uniform framework. So for a number of good reasons, we agree that we should use music. And there's no essential change because the bulk between visual and music are essentially almost the same. And this is about the local charge conservation background. I think by now there's a better way by Dima and Fokker, namely the so-called particularization sampler. So we will replace the more phenomenological local charge conservation by a more rigorous particularization. Again, in terms of measurement, they're going to be pretty much the same. And then the last difference is that your KMD is replaced by SMASH. This is just an improvement. You may say an upgrade. Again, I don't think there is any essential difference.
Okay, very good.
Yeah.
Okay, very good. Then let's thank Jinfeng again.